Today we begin a unit where we think about the distributions of the probability. So instead of thinking about just one particular value and the probability of one thing happening, we look really at all possible probabilities within the range. So today's title is 7.1, Probability Distributions. Quick discussion here. If you have moved your player on a board game according to the roll you make with the dice, how far do you think you would have moved after 5 throws? So what you might do is grab a die and roll it 5 times and add up the sum and just see how far you go. So how far do you think you would go? Pause the video and think through this possibility. All right, now that you've hopefully tried this out or thought through it, one thing you might think to yourself is that, what would the average roll be that I would expect on a single roll? And so with the numbers 1, 2, 3, 4, 5, and 6, if you add those all up and divide by the number of sides, which is 6, you'll get that the average side, the sum, or the value of the average side would be 3.5. And so the reality is we expect to move about 3.5 spots forward for every roll. Of course, you can't actually move 3.5 spots in most games. Neither will the die ever land on a side called 0.5. So you would expect after 2 rolls that you would be at 3.5 plus 3.5, which is 7. Or after 5 rolls, you would be at 5 times 3.5, which is 17.5. So you'd expect to be around spot number 17 or 18. Now, if you're a little lower or a little higher, that's not like you've blown things away, but around 17 to 18 is normal. Probability distributions can only be done with continuous variables. So a continuous variable is one that can take on any value. Okay, a discrete variable, however, can only take on certain values. Okay, there's really not an infinite number of options, whereas continuous there is an infinite number of possibilities. A discrete variable often might be limited to integers or specific types of numbers. Another definition for today is the term fair game. A fair game is one in which the expected value is 0. So a fair game with you and a computer would give each of you an equal possibility at winning. And if it wasn't equal, if the computer had an advantage, then it wouldn't be considered a fair game. And any casino is playing an unfair game. They have the results rigged so that they will make sure that they win against you. And all lottery corporations work that way too. That's why they make millions and billions of dollars, these different organizations. Let's quickly classify each of the following as discrete or continuous. The number of phone calls made by a salesperson. Well, you can only take on specific values like 1, 2, 3. You can't take on 1.5 or 2.5. So this would be considered discrete. The length of a phone call made by a salesperson. Well, I could take on 3 minutes and 52 seconds, 0.41 milliseconds or something like that. And so it can take on a whole bunch of values, actually an infinite number of values. And so this is called continuous. A company's sales can only take on dollar values, and dollar values are limited. You can't go beyond the penny, or maybe now beyond the nickel, really. And so a company's sales would be considered discrete. The number of computers sold by a company. Well, you can only sell whole computers, so that is also discrete. And the distance to the front of the classroom, that would be continuous, because you could measure it in meters plus centimeters, then you can go down to less than that, to the millimeter, and then even less than that. And so you could be very, very exact in this reality. Okay, let's look at some examples of probability distributions. So Expected value, the definition E of x, is the predicted average of all possible outcomes. So here's method one. To predict the expected value, we're going to do x1, which is my random variable, times the probability of that variable. Then plus x2 times the probability of it. And we keep going until we've taken care of all possible values. So let's consider a simple game in which you roll a single die. If you roll an even number, you gain that number of points. And if you roll an odd number, you lose that number of points. So even when you gain, and odd you lose. What is the expected value, expected number of points per roll? So for A, we're going to put down this. So the first thing I could roll is I could roll a 1, which has a value of -1 because you lose points for odd numbers. And then what's the probability of getting that side, the 1? Well, there's a 1 in 6 chance. Plus the probability of getting a 2. And the 2 is positive because we gain points on that. And there's a 1 in 6 chance of getting that. If you roll a 3, you lose 3 points. So we'll subtract 3 times the probability of that, 1 in 6. If you roll a 4, you gain that. Probability of it, 1 in 6. If you roll a 5, you lose. Probability, 1 in 6. And if you roll a 6, you gain it. Probability is 1 in 6. In that long line there into your calculator, you'll find that the value here is 0.5, which means the expected value is positive, and actually you're expected to move forward in this game. And that makes sense because if you actually group these together, probability of getting a 1 and a 2 is equal. And if you get a 1, you lose a little bit of points, but if you get a 2, you gain more. And same thing for a 3 and the 4. If you get a 4, you gain more points than you lost if you had a 3. And same thing for the 5 and the 6. And so, yeah, you are expected to actually gain spots forward in this game. So the question is this a fair game? No. You are expected to gain points. And yeah, if you're playing against yourself, who really cares? But if this was a game where you said, I'm going to take evens and the other person's going to take odds, well, you just rigged the game in your favor, and that's not fair as a game. Okay, let's look at another example. Here we're going to look at lottery tickets. So the Super 7 has the following winners on Friday, April 17, 2007. This is real. The tickets cost $2, and the total number of tickets sold were 1,319,173. So what we're going to do is we're going to find out the expected value using this formula right here. Okay, this is revenue. So here, our revenue is how much money they take in. Well, they sold the tickets at $2 each, and they sold 1,319,173. So their revenue is $2,638,346. Okay, now their cost. Well, their cost is, well, there's some hidden costs, and I'm not going to deal with that. So there's hidden costs of having to have companies sell their tickets and all that stuff. But let's just look at these actual dollar values that we have in front of us. So the specific cost here would be giving away prize money. So if they give away 0 tickets of the 0 winners in the $10 million, they didn't have to pay anything there. But if they gave 2 winners at $93,112, then that means that cost them $186,224.40. And that was simply by multiplying those two. Same thing with the next. We have 103 winners who won $1,808. If you multiply those two together, you actually get the same amount again. Okay? And next, there is 5,933 winners of the next at $106.70. That would cost them $633,000 $633,051.10. And then here we have $10, and that would be $1,269,970. And here you multiply again, and you get $1,161,530. And the sum here will give us the total cost that they have. So their total cost was $3,436,999.50. All right, so our expected value is the revenue, $2,638,346, minus the cost, which is $3,436,999.50, divided by the number of tickets, which is 1,319,173. And then you'll get the cost of negative 0.61 cents. So this formula is written from the perspective of a lottery company. So I don't know why I called this C, but I did. So that's C, and this is D here. So what does this actually tell you about the profit for the Super 7? Well, we can see that their revenue was $2 million, just over $2 million. And their cost was over $3 million. So we know that Super 7 lost money on this day. Okay? But before you feel bad for them, remember these companies are making money, massive amounts of money. So they don't mind losing a few dollars one day. And and they will gain lots on another day. Okay? Just to illustrate something, you can use that other formula. So the other formula was E of x equals x1 to the probability of x1 plus x2 times the probability of x2 plus, and keep going. The problem with this, and it works, the first value was 10 million. And the probability of that was 0 over 1,319,173. The next one was valued at $93,112.20. The probability of that was 2 people got that over 1,319,173. And we just keep going. Now what's missing in this data is this last set, which is there was a whole bunch of people who gained negative $2. They actually lost money on this, and they never list on these sites the number of losers. So the question is right here, how many losers are there? Well, all you need to do is add these up and subtract the number of tickets they sold, and you'll find the massive amounts of losers who play these games and lose on a regular basis. And so that's how you would use that other formula. So we got to figure out how many losers are there out of the 1,319,173. See that I have a wrong number right here. Okay, so that's another way you could do it. I don't suggest using that method. I really do like this method right here, the revenue minus cost over the number of tickets. And that is probability distributions.